Now we're going to talk about basis and dimension. So I've been talking about the dimension of a vector space quite a bit, and I haven't been very precise about that. I think everybody knows what I mean. R2 is two-dimensional, R3 is three-dimensional, a plane is two-dimensional, a line is one-dimensional. That's all clear. But we need to go back and look at that in more detail and make that precise. So that's what the next discussion will be about. So here's the idea. The basic question is, how do you tell if you have extra vectors? And what do I mean by extra vectors? Well, suppose that I had two vectors, v1 and v2. And suppose they spanned a plane. So I'm in some vector space. It doesn't matter. It could be a big vector space of high dimension. But let's suppose that these two vectors span a plane. So I'll just draw the plane roughly like this. And suppose I had a third vector in that plane, v3. Well, v3 is what I mean by an extra vector. And what I mean by that is it doesn't contribute anything to the span. The span of v1, v2 is just the same as the span of v1, v2, v3. It doesn't get any bigger by adding another vector in the plane. Well, by contrast, suppose I started with the same v1 and v2, and my vector v3 pointed off outside the plane in some other direction. Well, now this third vector is not extra. The span of v1, v2, v3 is bigger. I should say the span of v1, v2 is smaller than the span of v1, v2, and v3. So that's what I mean by a vector being extra or not. And we need, well, that's a picture, so let's make this a little more precise. And that leads us to a key concept in linear algebra, which is the following. So I have a vector space, and I have some vectors in it, v1 through vr. Now here's the definition. It's got two parts. First part is, suppose I can find scalars c1 through cr. And now here's the key thing. They're not all allowed to be zero. At least one of them has to be non-zero. Suppose I can find such scalars such that linear combination of these vectors is the zero vector. Then we say that these vectors are linearly dependent. So there's a relation like this, the sum is equal to 0, and it's a non-trivial relation. At least one of those coefficients in that expression is non-zero. Well, the opposite case is the vectors are linearly independent. And, well, let's express that like this. Suppose I have an expression like this. C1, the linear combination of these vectors is 0. And suppose the only way I could do this if all of the CIs are 0. Obviously, if all the CIs are 0, it makes this true, but if that's the only way to make it true, then it's the opposite case, and these vectors are said to be linearly independent. Okay, so I suggest you pause the video here and think about this a little bit before we go on. These are important concepts. Okay, so let's look at an example. Well, I'm going to do a really basic example. Take v as r2 and take these two vectors, 1, 0 and 0, 1. Let's check. Are these linearly independent? Well, suppose you had an expression like this, where the sum is 0. Well, let's just write that out. That would say that this sum is equal to 0. And if we combine those into one vector, that says this vector is equal to 0. Well, that means that both c1 and c2 have to be 0. So since both coefficients are forced to be 0, that says that these vectors are linearly independent. And the picture is that they're pointing in different directions. So there's no way you can add one to the other and get 0 unless You just take all coefficients 0. But by contrast, suppose you took these three vectors. You took the first two we just had and added the vector 1, 1. Well, that's the extra vector. And these are, let's check, are these linearly independent? Well, here's a relation. You can add these three vectors with a minus sign in front of the third one and get 0. And not all of the coefficients are 0. Some of them are non-zero. Well, in fact, all of them are non-zero, but that doesn't matter. At least one of them is non-zero. So that says that these three vectors are not linearly independent. They are linearly dependent. So you see that this notion exactly captures the notion of extra vectors. Here's a slightly different way to think about linear independence and dependence. A bunch of vectors are linearly dependent if and only if one of them, I'm not sure which one, but one of them, vi, is a linear combination of the others. So again, that's sort of reinforcing the extra notion. The v3 isn't really needed because it can be written as a sum of the other two. So in our example, we had the relation that v1 plus v2 minus v3 is equal to 0. That shows that these vectors are linearly dependent. Well, just put this guy on the other side, and that says that this vector is the sum of those two vectors. All right, the last thing I want to do is talk about something about independence and dependence, which comes up in the setting of row echelon matrices. So let's just look at an example. Suppose you had a matrix in row echelon form like this. So it's in row echelon form, but not reduced row echelon form. And look at the two pivots. And now there are two things which are clear in this example. So the first is that if you take the two non-zero rows, they are linearly independent. So in this case, 1, 2, 3, 4 and 0, 0, 2, 5. I'll leave it to you to convince yourself that's true. It's quite clear. And also, the two columns, including pivots, are linearly independent. So that is to say 1, 0, 0 and 3, 2, 0. And again, this is quite clear. Well, this is just an illustration of the general fact. If you have matrix A in row echelon form, and reduced or not, it doesn't matter, then, first of all, the non-zero rows are linearly independent, and the pivot columns are linearly independent. That's two different sets. The rows and the columns are each linearly independent. And the number of these is the rank, which is to say the number of non-zero rows and the number of pivot columns is equal to the rank. Well, all I'm saying is that the rank is the number of pivots. But it's kind of interesting that we get two linearly independent sets, one involving the columns and one involving the rows. And that's going to be important for us later. So that's a good place to stop, and I'll see you in class.